私は司会させていただきます、京都大学理学部物理教室の前野と言います。よろしくお願いいたします。今日はアンソニー・レゲット教授に東大特別講義ということで、午前中はノーベル物理学賞に講演に関する講演をしていただきました。午後は、時間の矢というタイトルで、お話しいただきます。それで、簡単にですね、レゲットさんの兄弟物理の伝統に従って、あえてレゲット先生じゃなくてレゲットさんと呼ばせていただきます。レゲットさんのご経歴を紹介させていただきます。特に京都大学の物理学教室とも関わりを持っておられます。レゲットさんは、ロンドンの近郊で1938年にお生まれになりました。そして、学部生の方も多いと思いますが、オックスフォード大学に、今でいう飛び級で入学されまして、当時一番学問としてハイクラスレベルというような認識があったそうなんですけど、クラシック古典ですね、ラテン語、ギリシャ語に基づいて、哲学研究、それで学部の学位を取られました。でしかし卒業する直前になって物理学を第2の専攻としてですね、学部の第2ディプロマとして専攻されまして、両方のクラシック古典と物理学とで卒業されました。そしてその後オックスフォード大学の大学院にそのまま進まれまして、指導教員は教授はテルハール教授の下で、博士論文のタイトルはヘリウム、超流動ヘリウム4における炎の研究、そしてもう一つのトピックとしては、上流動のヘリウム3の中にほんのわずかヘリウム4を入れた、そういう経緯の性質について研究されました。そして博士を取られて1964年5年の頃は、イリノイ大学アーバナ・シャンペーンUIUC といいますか、アメリカのイリノイ大学でポストドクター博士研究員のを取られました。そして1965年の秋から1年間、京都大学に、物理教室の、京大理学部物理の、松原武雄教授のグループで、常蔵教授が若い頃にそれは1965年ですから、東京オリンピックの確率で、建築ラッシュで物理教室もちょうどその時に南館というのを建設していた頃だと思います。建設があったと。今物理教室で1年間おられました。そしてその後67年からはサセックス大学、そして83年からはイリノイ大学に戻られまして、イリノイ大学の教授として30年間おられました。で、レゲスさんは超流動、超伝導の研究で非常に著名ですけれども、そしてもう一つ非常に著名なのはマクロな経での、特に散逸がある経での量子力学、量子的な振る舞いという、そういう物理学の分野を先導する研究をされました。で特に超伝導のジョゼフソン接合であるとか、そういう凝縮系の経を使って量子力学の基礎を検証すると、そういう研究の理論研究をしてこられました。そして、非消失ですね、グラスといいますが、非消失体の低温での振る舞いであるとか、最近はボーズ・アインシュタイン凝縮ですね、冷却気体のボーズ・アインシュタイン凝縮の研究でも、非常に著名な成果を上げておられます。で、この3年間はですね、日本学術振興会の、招きで、東京大学で1年間に1ヶ月滞在して集中講義をされております。で今年で3年目になると思うんですけれども、ですからこの後東京大学の方に行かれて講義がオロジカル量子計算という講義を大学院生の講義をされます。で、今回は私の方がグループリーダーさせていただきます、新学術領域研究トポロジカル量子現象というプロジェクトがあるんですが、その外国人アドバイザーの一人になっていただいておりまして、3年間ですね。でそういう経緯もありまして、京都にも立ち寄りいただいて、今回の特別講義をしていただくということになりました。でこの午後の講演に関しては低温物理学、低温物理科学で低温物質科学研究センター LTM センターの共催をいただいて実現しましたので、お礼申し上げます。ということで、では講義を始めたいと思います。席の方がまだそちらに少しあります。立っておられる方はそこに席がありますので、どうぞ座ってください。後のまた遅れて来られる方のためになるべく後ろの方は、前に席がありますので、ぜひお願いします。それでは、Please welcome Professor Leggett。レゲットさん、よろしくお願いします。
50年ぶりに変わってくるのを嬉しく感じます。だけど、残念ながら、50年の間に日本語は大体忘れました。この講義を英語でやらせていただきます。ゆっくり話すことにします。Okay. One of the most common and everyday features of our experience of the physical world is the fact that we can remember the past and affect the future, and not vice versa. How nice it would be if I could go back to that party the other night and correct that awful social gaffe that I made. But, alas, I know I can't. How nice it would be if I could go forward in time to the horse race tomorrow afternoon, foresee the winner, and place my bets accordingly. Again, unfortunately, I know I can't. So this fact that we can remember the past and affect the future, and not vice versa, that is, that there does seem to be a definite arrow of time which flows in a particular direction. It's a very everyday part of our experience. Connected with this, but not quite the same point, is that if we see a movie of some everyday scene, we can usually tell whether it's being shown forward or backward. Let me try to illustrate that. Now, let's see, I'll just press the... Yeah, okay. So we have the first video, please. Now, this video concerns two of our lab assistants at the University of Illinois. They're quite athletic people, but not Olympic quality. So just watch them, and in particular watch the little jump at the start. There you go, you see? Okay, that's one of them. There she goes, yes, there she goes. Right. Well, maybe it's plausible, maybe not, but can we have the second one, please? Now I think you know which way was the right way round and which one was backwards, right? The next one is perhaps even clearer. Perhaps we have the next one. Okay, that looks all right, doesn't it? Now what about the fourth? So something wrong, right? Okay, so we can all tell when the arrow of time, as it were, is reversed. So why should this arrow of time, or jikan no ya, why should it be a problem? Well, to see why, let's just think about the elementary laws of physics. Can we go to the first actual slide now? First text slide. So I just no. So we want the first text slide. Okay, good, fine. Good. Okay, the problem is that with one very small exception, which I will mention briefly, the microscopic laws of physics, that is, the laws of physics, as we know them, at the level of atoms and molecules and so forth, don't seem to make any distinction between the forward and backward direction of time. Let's first think about Newton's laws. Now, I'm sure you're mostly familiar with Newton's three laws. Newton's first law says that every body remains at rest or in uniform motion so long as no external force acts on it. Well, there's no reference there to whether time is flowing forward or backward. Newton's third law says that every action is accompanied by an equal and opposite reaction. Again, no mention of the direction of time there. So if there is any reference to the direction of time, it has to be in Newton's second law. Newton's second law says that force is mass times acceleration. The force, for example, might be due to gravity, for example, the gravity of the Earth. And fairly obviously, there's no reference to the direction of time there. Again, mass, fairly no reference. So if there is any reference to the direction of time, it has to be in the concept of acceleration. Now, acceleration is the rate of change of velocity. Suppose time is run backwards, then velocity is reversed. For example, suppose that I'm standing on against the wall of a merry-go-round. And suppose that the merry-go-round is rotating clockwise. Then the velocity is in this direction. Now, I will feel, under those circumstances, I will feel an acceleration towards the centre of the merry-go-round. I know that because there will be a force pressing against my back. And perhaps some of you have perhaps been to this machine in a fun fair where they press you against the wall of a rotating cylinder and then drop the floor away, and you're stuck against the wall and you continue to rotate. Okay? So definitely the acceleration, the force you're experiencing, and therefore the acceleration you're experiencing, is towards the centre. Now suppose that we run the merry-go-round backwards. Now the velocity is reversed. However, you will still feel the same force on your back, pressing you towards the centre. So the acceleration is the same, despite the fact that the velocity has been reversed. So, in other words, Newton's three laws, all of them, work just as well backwards as forwards. They will not enable you to say which way round time is flowing. Well, you say, okay, that's fine, but that is just mechanics. What about electromagnetism? For example, suppose I have a magnetic field in the vertical direction. And imagine I have a charged particle, such as an electron, which is moving in this field. Then the electron will perhaps circulate anti-clockwise around the field. So you say to yourself, fine, now if I show the movie backwards, the electron will be moving this way. And so I will know the difference. No? There's a catch there. Where did the magnetic field come from? The magnetic field was produced by currents in certain coils in a magnet. The currents are electrons flowing. So if I reverse the direction of time, I must reverse the direction of the current. The magnetic field is no longer up, but down, right? And so, indeed, the electron will circulate clockwise, but so it should. We will not be able to tell the difference. Some of you might have met quantum mechanics, and at first sight, at least, in quantum mechanics, it does look as if there's some reference to the direction of time, because the way that textbook problems are normally formulated is that they say, okay, they give you the quantum mechanical state, the wave function, at some initial time, and then they integrate Schrödinger's equation forward in time, and at the end of a certain period, they make a measurement and read off the results. So at first sight, it looks as if the direction of time is quite important there. But that's not really the case. It's a very famous paper by Aharonov, Bergman, and Lebovitz, nearly 50 years ago now, where they actually show that it's perfectly possible to formulate quantum mechanics in a way which is completely symmetric with respect to the direction of time. And then by making certain assumptions, you can get the usual quantum mechanics or a sort of time reversed version. But the basic formulation is time symmetric. So most of the laws of physics at the microscopic level don't seem to know the difference between the forward and backward direction of time. Now, there is one exception. There is one kind of collision which we nowadays can produce in high-energy accelerators. And it does look as if that particular kind of collision does know the difference between the forward and backward directions. In fact, so that if you were to show a movie of the collision process, in principle you could know whether it was being shown backwards or forwards. However, that's a matter of relatively recent discovery. In fact, it's only a few months ago that it was actually verified with certainty experimentally. So it's certainly a very, in some sense, not at all an everyday phenomenon. Most people, including me, believe that peculiar asymmetry in high-energy physics is not really relevant to the kind of problem I'm going to be talking about today. It's conceivable we could be wrong, but right now that certainly seems the majority opinion, and I will assume that. So for the rest of this lecture, I will ignore that slight complication. Okay. So now connected with this this question of the symmetry of the laws of physics, and the second question, again related but not quite the same. Okay. I think we skip a couple of movies perhaps here and go on to the next text slide. So can I do that? Yeah, fine, good. The question is there any basis in microscopic physics for the idea that the past causes the future rather than vice versa? Well, imagine that we consider a simple textbook problem here. Here, for example, is a cannon, which is going to fire a cannonball. And the way that the problem is usually formulated in mechanics textbooks is that the book gives you the initial position and velocity of the cannonball. And then it invites you to calculate the subsequent trajectory of the cannonball, so that, for example, it will ask you to calculate the intermediate position and velocity and perhaps the final position and velocity. So, in other words, if we know the initial position and velocity, we can determine the exact trajectory. We can determine the whole behaviour of the cannonball in the future. So that tends to suggest that, in some sense, these initial conditions cause the subsequent motion. And this is the basis of a very famous thought experiment due to the French mathematician and physicist Pierre Simon Laplace in the early 19th century. Laplace said to himself, let's consider a demon whose faculties are so acute that at a particular time he can determine the positions and velocities of every particle in the universe. And moreover, let's suppose that this demon knows all the forces acting. Then the demon would be able to exactly foretell the whole state of the universe for the complete future. You know, the whole future of the universe. And for many people, that thought experiment has seemed a strong argument against the idea of free will. I thought I just raised my arm voluntarily. But if you really take Laplace seriously, then a demon who knew the positions and velocities of every atom in the universe, including those in my brain, 10 minutes ago, could have foretold exactly that I was going to raise my arm at this time. And therefore my impression of possessing free will is an illusion. Well, there are all sorts of things one can say about that argument, but here's one thing, I think, which one ought to say. Going back to this original textbook thought experiment, Newton's second law is second order in time. So technically that means that any two independent pieces of information will suffice to completely determine the solution. So, for example, if I know the final position and the final velocity of the cannonball, then I can work backwards in time and determine its complete trajectory, including the initial position and velocity. Again, if I know the intermediate position and velocity, I can work both forwards and backwards and determine the whole trajectory. And so, at least within the context of Newtonian mechanics and the rest of microscopic physics, there really is no basis for the idea that it's the past which is causing the future, and not vice versa. They come in exactly the same footing. Well, okay. This puzzled a lot of people, particularly in the early 19th century. And eventually, a very brilliant group of scientists, physicists, and engineers, mostly French, came up in the early 19th century with a kind of solution to this problem, or at least a different approach to this problem. And it's based essentially not on considering single particles and their behaviour according to Newton's laws, but large collections of particles, let us say atoms. So, what are molecules? Let's imagine, for example, we have a large number of molecules which are confined in one half of a box. The box is separated into two by a partition, which, however, can be withdrawn. Well, initially we've confined the molecules on this side, and of course, so long as the partition remains in place, they will stay there. However, let's suppose that sometime we pull away the partition. Then we all know, and sometimes almost common sense by now, that the molecules will expand to fill the whole box. And now we can wait as long as we like, but as long as we don't do anything drastic to the system, there is no possibility that the atoms will all spontaneously reverse and occupy this state. Why? Well, intuitively you say, look, there's a lot more ways the atoms can dispose themselves here than here, so why should they voluntarily go back to this very small number of states they have here? And now I'm going to illustrate this point with an example which I can use freely in the United States when I give this lecture. I'm not entirely sure that I can use it freely in Japan because I'm not sure that everyone will have had the relevant experience as they all have in the United States. But anyway, this analogy is related to parking. If you have in fact taken a driving lesson, you will, I think, understand this very well. suppose you are taking your first driving lesson, and the instructor takes you to the school car, which is parked by the sidewalk, and he instructs you to drive it out into the road. So you have no particular difficulty doing that, generally speaking. But now at the end of the hour, he brings you back to the same point, and he instructs you to park the car by the sidewalk here. You all know that that is much, much more difficult. Right? Well, why is it more difficult? Well, fairly obviously, because in some sense, here, the state you're trying to attain is a very large time space. In other words, there are many possibilities as to where you could actually emerge into the road. Here, on the other hand, you have to get back into a single state, or at least a small set of states along here. So, in some sense, it's very easy to go from a small initial state, space to a large final space, and vice versa. Now, in physics, we try to formalize this idea by introducing a quantitative measure of the number of states, or, as we sometimes say, the degree of disorder. Now, at first sight, one could just define the disorder as the number of available states, or the amount of available space. But for technical reasons, we prefer not to do that. We prefer to define the degree of disorder as proportional to the logarithm of the number of states. As I say, the reasons for that are technical, and I won't try to go into them. And in physics, we postulate a quantity called entropy, which is usually denoted S, and that is supposed to be, in some sense, a measure of disorder. And more quantitatively, we say that the entropy, S, is a particular constant, nowadays called Boltzmann's constant, times the logarithm of the number of available states. And this is usually called Boltzmann's equation, related to his name. And then the famous law of thermodynamics, second law of thermodynamics, tells us entropy always increases with time. And at first sight, that seems very natural, because after all, we all know that it's much easier to go from a state with a small number of states, that is with low disorder, into a state of higher disorder. And if any of you are parents and have ever left your small child alone to play in a room which is filled with various objects, you will readily appreciate that disorder does tend to increase in time. So at first sight, this is a very common sense explanation of the origin of time asymmetry. It is the forward direction in time is simply the direction in which disorder is increasing. And you think, wait a moment, it's not quite so simple. Unfortunately, many standard textbooks basically leave it at this point and give you the idea that they've explained the direction of time. Let's stay there. Let's go on to the next slide. Imagine the following thought experiment. I have here a machine which is designed to shuffle a deck of cards. You all know what that involves. This machine is enclosed in a locked room, every time it shuffles the cards, it displays the results on a table here. And we have a camera. One of the functions of the camera is to make sure that no super Houdini sneaks into the room and disturbs the experiment. But the other function of the camera is simply to record the different arrangements of the deck of cards. So this machine will be shuffling the cards. Every time it's done one shuffling process, the camera will take a photograph of it and record it and go on and do the next shuffling process, and so on. Now imagine that we've set this machine in motion and it's shuffling away, and we go off to lunch. And we come back from lunch and inspect the picture which the camera is currently showing. And to our great surprise, it shows something like this. Ace, king, queen, jack of spades, ... perfectly ordered set of cards. What would we conclude? Well, obviously, the most obvious conclusion is that indeed some kind of super Houdini has slunk into the room and managed to evade the camera and prepared the cards in this way. That's the obvious common sense assumption, right? But suppose that somehow we manage to convince ourselves that that's not right. Then what can we conclude? Well, the most obvious thing we conclude is that as the shuffling process proceeds in time, the deck of cards will get steadily more disordered, as it's doing in this figure here. Right? So indeed, disorder will increase in time. Now we think, wait a moment, what happened earlier? Well, after all, the inverse of a shuffling process is itself a shuffling process. So what that means is that if we're given that at 12 o'clock, say, the cards were perfectly ordered, then we know for sure that at 11:55 they were more disordered, and will get further disordered as we go back into the past. In other words, in this case, disorder will be decreasing in time. So why don't we usually say that? Well, at first sight, it's because we all know, as a matter of common experience, that as human beings, we can physically prepare a definite arrangement, like cards say, and then let nature take its course. What we don't seem to be able to do is what you might call retro-repair. That is to set final condition here and watch what happens as we go backwards in time from that. So at first sight, that would seem to connect the asymmetry of time with what we as human beings can or cannot do. But this already is getting, as you see, a somewhat circular argument. And worse, in any case, it can't be the whole truth, because there are many processes in which no human being is involved, where we can still recognise the arrow of time. Let's take a look at one of those. Suppose, for example, we have a rock which is perched unstably at the top of a cliff. After a time, erosion takes effect. The rock detaches itself from the cliff, rolls down the cliff face, falls into a lake at the bottom, and waves radiate outwards to infinity. And eventually, the rock will settle on the bottom of the pool. Now, suppose that we were shown a movie in which the rock starts at the bottom of the pool, spontaneously lifts itself to the surface, the waves come flowing in from infinity, the rock rolls back up the cliff and reattaches itself at the top. Of course, we would know that this is shown the wrong way round, despite the fact that no human being is involved in this picture. So it can't be quite that simple. At this point, let's just try to review the various possible manifestations of the arrow of time as we know them in everyday life and in physics and cosmology. Before I do that, I'm sorry, there's one important point I want to tell you about. This is not a new problem. People have been worried about this problem ever since the middle of the 19th century, perhaps even earlier. And one of the people who worried most intensely about it was indeed Ludwig Boltzmann. Here is his tombstone in the Central Friedhof in Vienna, in Austria. And ironically, above his bust is inscribed the equation S equals K log W, which I showed you earlier. The reason it's ironical is that apparently, historically, there was no evidence that Boltzmann ever wrote that equation down, even though it is very closely associated with his ideas. But he didn't actually write it down. Nevertheless, we call it Boltzmann's equation. Anyway, I say Boltzmann thought very, very hard about this problem. And he actually came up with a very, very clever solution, which amazingly anticipates ideas from nearly 200 years later. And here's roughly how Boltzmann's solution goes. Boltzmann said, well, look, we know that on average, the state of the universe will always tend to the state of maximum disorder. So for most of its time, you have to remember, incidentally, that in Boltzmann's day, people didn't know about the Big Bang. They thought that the universe was more or less time independent and static. So on the whole, on average, the universe will be in the state of maximum disorder, that is maximum entropy. But occasionally, but also, having invented basically much of the what we now call statistical mechanics, Boltzmann also realised that there was a small but non-zero probability that a small region of the universe would, from time to time, fluctuate away from the state of maximum disorder into a state of somewhat higher order, that is lower entropy. So imagine that a small part of the universe in which we happen to be sitting has fluctuated away from this state of maximum disorder. Well, of course, eventually it's going to go back to maximum disorder. But now suppose that we are actually living at this point on the curve. Then we will see disorder increasing in this direction. And therefore, that will be the direction of the future as we perceive it. If, on the contrary, we had been living on this part of the curve here, then we would see disorder increasing in this direction, and we would have said this is the direction of the future. Well, so far, so good. Now, then, of course, the question arises, why should we be sitting on this part of the curve at all? After all, the vast majority of the universe at all times is in this state of maximum disorder. So how come that we're actually sitting on this very improbable fluctuation? And then Boltzmann gave to this a very remarkable answer. He said in effect, well, if we were sitting on this part of the curve where disorder is a maximum, then the conditions for chemistry and biology and so forth, as we know them, would not be there. So in other words, there would be no question of human beings being produced. We would not be there to ask the question. So the reason, as it were, that we are living in this particular improbable part of the universe is that if we were not, we would simply not be here to ask the question in the first place. And this is remarkable because it's an anticipation of a rather interesting principle which is quite widely discussed in physics nowadays in a slightly different context, namely the so-called anthropic principle. According to our current ideas of high-energy physics and cosmology, there are a number of fundamental constants, dimensionless constants, which we have to include in the theory, but for which we have no particular explanation. A typical example would be the ratio of the mass of the electron to the mass of the proton. It's about 1 to 1,800. Now, that number seems very firm, very fixed. Right now, we don't know why it has that value. Perhaps some future theory will find a good reason why it has that value, but right now we don't know why. And so a rather popular point of view among some high-energy physicists and cosmologists is to make the observation that if that mass ratio were just different by a tiny amount from what it actually is, even if it were different by, say, 0.1% from its actual value, then in fact it turns out that the structure of atoms would be quite different from what it currently is. Certain molecules could not form. Chemistry, as we know it, and biology could not get off the ground. And therefore, again, we would not have evolved to ask this question. So as I say, this is sometimes called the anthropic principle. Anthropos is the Greek word for man, mankind. And people argue furiously about whether that is a real explanation or not. But in any case, it's very interesting that Boltzmann anticipated this by nearly 200 years. Now, why don't people nowadays tend to take Boltzmann's solution too seriously? Well, the problem is that Boltzmann did not have space stations and he didn't have space telescopes or satellites. And therefore, the part of the universe which he could actually see was very tiny from a modern point of view. Nowadays, we can see out to billions of light years in all directions in the universe, and it doesn't look as if our part of the universe is in any way special or improbable. In fact, it looks as if our from a cosmic point of view, our immediate neighbourhood is very boring and very similar to many other neighbourhoods. So the idea that we are part of a very special fluctuation doesn't really seem very plausible. And if it were to work, we'd have to be part of a really, really enormous fluctuation. And most people don't really like that idea. Okay, let me go on to this point to discuss the various manifestations of the arrow of time, as we know in everyday life and in physics and cosmology. So I've excluded here that what's usually called the CP violating arrow. That's the very special one that I talked about earlier. So let's forget about that. What manifestations of the arrow of time do we know? Well, the first obvious one is the psychological one, which we mentioned. We can remember the past and affect the future, not vice versa. Again, there's a biological arrow. Generally speaking, plants or animals tend to start small, they grow bigger, and eventually in one way or another they wither away and die. There's the electromagnetic arrow of time. Now, okay, at this point, perhaps we could just have the last pair of movies, the last two. Yeah. Okay, now the laws of electromagnetism. Yes, please. Change yes. Okay. Now this is this is actually not electromagnetic radiation. This is a photo of two sticks oscillating in a pond, but it's the same principle. Okay, so the radiation waves are going out, right? However, the laws of physics are completely invariant under time reversal. In other words, the time reversed version of this should be equally valid. Could you do the next one? Yeah, you see, that's an equally valid solution of the equation of motion. And yet it doesn't seem to happen. And in particular, in the case of light waves, it doesn't seem to happen. Whether we're talking... Okay, thank you. Go back to the slide now. Not only... I think it's a non-trivial fact. Not only man-made objects like light bulbs, but also natural objects like stars seem to always be emitting radiation, not absorbing it. Again, there's the thermodynamic arrow, which we've already met, the idea that disorder or entropy increases with time. And finally, the so-called cosmological arrow, which, as we'll see, is a little different. What that means is that, at least as far as we know right now, the universe seems to be expanding rather than contracting. So that, again, is a manifestation of the arrow of time. So now we can ask the question, is there any obvious relation between these? Can some of them be regarded as consequences of others? Well, let's take first the relationship between the psychological and the biological arrow. I don't think there's anything logically absurd about the idea that I might be able to remember the time when I was leaning on a stick and my hair was even whiter than it is now, and affect the time when I am small, this size, and schooling in my mother's arms. Nothing logically absurd about that idea. However, most people I think would guess that are very good neuropsychological and biological reasons why that's not likely to be the case in reality. So, in other words, it does seem rather natural that the psychological arrow could be regarded as a consequence of the biological arrow. What about the electromagnetic, this relation here? Well, how do plants, and to some extent animals, grow? Plants certainly grow by absorbing incoming sunlight and converting it into chemical energy. Now, if the sun were sucking in radiation rather than radiating it, obviously this wouldn't work. So again, this is a rather natural connection between the electromagnetic and biological arrows. This one here, again, I think it's very plausible to try to regard the electromagnetic arrow as a consequence or a special case of the thermodynamic arrow. After all, in some sense, when the radiation is contained within the star, the number of available states is much less than when it's spread out to infinity, just as for the gas in the box. So again, it seems that we could regard the electromagnetic arrow as a special case of the thermodynamic arrow. Finally, what about this relation here? Now, this is the really tough one. So let's just go over to the next slide. Where we have hopefully, let's get past that one. Yeah. So the question can cosmology explain thermodynamics? That is the thermodynamic arrow of time a consequence of the cosmological arrow? Now, at this point, I have to admit freely that I am by no means an expert in this area. However, I'm not too embarrassed to be saying a few words about it, simply because the people who really are world experts in this area, the kind of names that you're all familiar with in popular books and so forth, they disagree furiously among themselves about this issue. So I'm not particularly hesitant to wade in. There's a very standard model of the universe called the Friedman-Robertson-Walker, or FRO model. And that model contains an important parameter, which is the mass density of the universe, the overall mass density expressed in particular units which make it dimensionless. And that's usually called capital omega. However, independently of this capital omega, all standard scenarios agree about the past. That is, they all predict that, or retrodict, that as you go back in time, the universe appears to be much more dense and much hotter. And if you go back far enough, you always come to a particular point, which is usually called the hot Big Bang. Formally, at that point, you find the universe has infinite temperature and infinite density. But I think probably a more appropriate way of putting it is that it's a point at which the laws of physics, as we currently know them, seem to break down completely. So anyway, all versions agree on that. So that raises the crucial question: is there any a priori reason why the disorder should have been low when the universe was very dense? In other words, why is disorder low at the small end? Is there any good a priori reason why that should be so? Now, it's certainly true experimentally. If we look at the cosmic background black body radiation, we can try to estimate the initial entropy of the universe, and it turns out that it's orders of magnitude lower than you would expect from, as it were, a random picture. In other words, in its very early days, it does seem that the universe was very, very highly ordered. The question is why? Is there any a priori reason for this? Well, as I say, the big names in the field disagree furiously about that. If you read some of the popular books which claim that it's, in some sense, almost natural, almost trivial, that its disorder is low at the small end, I would recommend you to read a rather good book by the Australian philosopher of science, Hugh Price, called something like Time's Arrow and Archimedes' Point, where he takes on head-on these arguments, and I think effectively demolishes them. Anyway, as I say, it is very controversial. But putting that aside for a moment, what about the possible futures of the universe? Well, we have three possibilities here. If this important parameter omega is smaller than 1, then at least until recently it was thought that the universe would go on expanding more or less smoothly forever. If omega is equal to 1, and you might think that's very improbable, but there are some reasons for believing it might be, then the expansion will gradually flatten off, and eventually, essentially, the universe will reach a steady finite size. Finally, I'm sorry, there's a typo here. If omega is greater than 1, then the universe will expand to a maximum size and eventually contract again, becoming much more dense and much hotter, and eventually will disappear into what is sometimes called the hot big crunch. Now that raises a very interesting question. Suppose that in fact the universe is closed. It probably isn't, in fact, but it's not absurd to assume it might be. In that case, it's going to expand to its maximum size and eventually contract again into the big crunch. The interesting question is, in this region here, we know it's getting smaller and we don't know it's getting hotter, but is the disorder increasing or decreasing? Furthermore, if human beings were still somehow alive in this phase of the universe, which way would they see the future? Would they see it towards the big crunch or away from it? Again, rather surprisingly, it turns out that people can't agree about this rather fundamental question. And again, I think this is where Hugh Price's work is very important. he basically makes the point that anything you say about the hot Big Bang, you have to say about the hot Big Crunch. And therefore, if it was natural that disorder is low here, it must also be natural that disorder is low here. And this you really can't get away from. And I think that's a good argument, by and large. So if that were right, of course, then what would happen is that disorder would be decreasing down here, and presumably any human beings alive would see the future in this direction. But as I say, that's still the argument. Well, so as I say, we really have a big question mark here. We don't really, I think, understand the answer, at least I certainly don't know. I think it's fair to say it's not very understood. So let's put that aside for a moment. Let's just assume that we somehow have found a reasonable explanation of the thermodynamic arrow of time in terms of the cosmological arrow. That still raises the question, could the arrow of time reverse itself locally and temporally? Now here I'm getting onto some really quite wild speculation, which are difficult to define, as you'll see. But think of the following analogy. Imagine a piece of iron. Now, as you know, and perhaps some of you might have heard my talk this morning, the electrons in iron can be thought of as like small magnets. And above the Curie temperature, that is in the so-called paramagnetic phase at high temperatures, these magnets are pointed in random directions. So there's no net magnetization. Below the Curie temperature, however, there's a very strong tendency for these magnets to point parallel. And so in the so-called ferromagnetic phase, you'll find that almost always the spins are pointing in a particular direction. Let us say along the direction of the external magnetic field. And yet, the basic principles of statistical mechanics tell us that every now and then there is a non-zero probability that a small piece of the iron will fluctuate away from that. In other words, the spins in that region will spontaneously reverse themselves and point in the opposite direction to the average. As I say, these events are rare, but nevertheless they do happen with non-zero probability. Now, could there be something vaguely similar that happens with respect to the arrow of time? In other words, despite the fact that overall the second law of thermodynamics works, and time is flowing steadily from past to future in some intuitive sense, nevertheless there are small regions of space over which, for small intervals of time, this process is reversed. In other words, that in some sense, within these regions, we could say, yes, indeed, the future is causing the present, and the present is causing the past. Completely contrary to our normal ideas. As I say, it's a very wild speculation, and what's worse, from the point of view of a professional physicist, is that it's almost impossible to quantify. Now, you see, this I think brings out a very general point. The really, really slippery questions in physics are not the questions where one has a well-defined question and merely has to try to find the answer to that question. Those are the easy cases. The really difficult issues in physics are the ones where you don't know what question you would be asked in the first place. These are really slippery questions, and I think this kind of speculation about the arrow of time falls in that category. It's extremely difficult to formulate sufficiently precisely that one might perhaps try to do some experiments to see if it works. But so one can raise the question, why on earth should anyone ever contemplate such a crazy idea? That over small local regions the arrow of time could reverse and the future could affect the present. Well, there are some reasons which are not so bad, actually. And one of them has to do with a very famous series of experiments which have been conducted over the last 40 years or so. Now, for those who happen to know about it, let me just mention these are the so-called EPR Bell experiments. And they refer to the following situation. You have an atomic source which will, a set of atoms which are excited and can decay emitting pairs of particles, in this case photons. So these photons are emitted back to back, and now you do the following. You arrange that each photon at this end goes into a switch which is randomly activated and can switch this photon into one of two measuring devices. Each of these two devices will ask the photon a yes or no question, and the photon will be forced to give an answer. So, for example, measuring instrument A might ask the question, photon the question, are you polarized vertically? Yes. Or horizontally? No. Right? On the other hand, measuring apparatus B might ask the photon a different question. It might ask the photon, are you polarized in this 45-degree direction or this 45-degree direction? And again, the photon will always say yes or no to this question. So you always do get a definite yes-no answer to your questions. The raw data then is the correlation between the answers given at this end of the laboratory and the answers given at this end. Now, it's an experimental fact that the first and uninteresting from the present point of view observation is that the observed correlations are in fact what is predicted by quantum mechanics. That, however, is not the interesting thing from our point of view. The interesting point is that the observed correlations are inconsistent with any theory of the so-called objective local class. And that theory, such a class of theory, is defined by the conjunction of three postulates about the physical universe, which at first sight seem to be just plain common sense. Okay, let me start with locality. That's any of you who have done special relativity will know about that. It is simply the postulate that if two events cannot be connected by a light signal or something slower, then they cannot causally influence one another. A very basic postulate of special relativity theory, being in some sense the whole theory of relativity is extremely well verified. Most physicists really hate to throw away that. Second postulate, well, you can phrase it in various terms. I've got here objectivity, but I'd rather describe it in rather different terms. In terms which I call, this is a rather technical phrase, I'm afraid, macroscopic counterfactual definiteness. It works like this. Suppose that a given photon it happens to be switched by this switch into counter B. Then either counter B will click or it will not click. That's a fact about the world. I can hear that with my unaided hearing. I can write down the result. I can record it in a computer, whatever. It's a fact about the world. No one, I think, would deny that. Now you say to yourself, wait a minute. I could have, or the switch could have, equally well switched the photon into counter A. Then, what are we going to say? Now we can make two statements here. I don't think they're the same statement, but try translating it in Japanese and see if it works. I think it still will work. Right? Statement number one is that under these unfulfilled conditions, these counterfactual conditions, it is a fact that either counter A would have clicked or it would not have clicked. And that, I mean, at first sight, that seems obvious, because after all, whenever you actually do switch the photon into counter A, then it does either click or not click. So, it was a fact that either counter A would have clicked or it would not have clicked. Fine. Statement number two, either it is a fact that counter A would have clicked, or it is a fact that counter A would not have clicked. Not quite the same statement. And if you make that second statement, you are basically affirming the principle which is sometimes called counterfactual definiteness. That is, in the language of philosophers, counterfactual statements have truth values. Now, let me just observe. This is a very, very commonsensical part of our understanding of the physical world. I say to you, had I woken up 5 minutes earlier this morning, I would have caught the bus. None of you doubt that that's a meaningful statement. It's either true or false. Again, it's essential to the legal system. The prosecuting counsel says to the jury, had the accused not pushed his victim down the stairs, she would still be alive today. That's a counterfactual statement. And the jury has to decide whether that's true or false. So in everyday life and in the legal system, we very definitely assume that counterfactual statements do have truth values. That's my second postulate. Again, pretty unsettling to have to give that up. What's important in this context is the third postulate. I've called it induction, but that's perhaps the wrong word. I should have just used the word usual error of time. The idea that the past causes the future, not vice versa. And so in particular, our switching the photon into one counter or the other here, cannot propagate backwards in time and affect what goes on at the source here. That's the application there. I say, if you agree to all three of these postulates, then you produce experimental predictions which simply do not describe the experiments. Yes?
I have a question about objectivity.
Okay.
Now, if you have an induction, and if you have the, you said that objectivity is that the counterfactual statement of a proof value.
Well, that's why, yes, I'm probably using the word objectivity wrongly, but that's what I mean by it.
I would like to make one point. If you have an induction like this, and if you have a left-hand side, if you have a new set on the left-hand side of the induction, the statement is always true.
I'm sorry? If I have
If you
a...
have induction, logical induction statement like this.
Yeah.
If you have a logical induction statement like this,
Yes, yes.
and if you have a vacant null set on the left-hand side,
So
a vacant set null set on the left-hand side of the induction, it's always true.
sorry, I'm afraid I didn't quite catch the...
Zero.
Oh, 0 set?
Yeah.
Well, sure, because anything.
And so the counterfactual argument is always true.
I'm sorry, I think we probably need to discuss individually, because I think this raises a rather point which philosophers have argued about quite a bit.
Yeah. So maybe we have to consider more carefully about how we would evaluate the counterfactual argument.
Well, okay, fine, but I think perhaps you can take it from me that that I believe the statement as I've made it is strong enough to derive this conclusion here. Yeah, okay. So the question is, could the outcome of the measurements propagate backwards in time and affect the initial state within this very limited context here? Well, that's formally, it seems that it's probably in some sense okay, and there have been various attempts to build scenarios along these lines. But I think the really difficult question is, can we somehow embed these islands in which, if you like, time is flowing backwards, into a more general picture of the world in which, on average, the second or third dynamics holds? That, I think, is the really difficult question. And it isn't, again, it's one of those questions where it's not even, one of those issues where it's not even clear quantitatively what question one really ought to be asking. It's very, very slippery. If it were to be the case, then I think it would have some interesting implications for free will. Again, I think I just raised my arm voluntarily. Laplace comes along and says, no, you didn't, because after all, had I known the exact state of the universe 10 minutes ago, I could have predicted with certainty that you would raise your arm at this point. I say no, you got it wrong. It is my raising my arm at this point which actually determined the state of the universe 10 minutes ago. And in other words, we sort of upset the usual concept about the arrow of causation in time. Again, I say, very difficult to think of any experiment which could be relevant to that conjecture. But let me finish anyway with a very general point. If we think about the really major revolutions in physics over the last 500 years, I think we will conclude that every one of these major revolutions has involved the abandonment of some idea, some assumption about the physical world, which up to that time had seemed the most obvious common sense. It's obvious the sun goes around the earth until Copernicus showed us otherwise. It's obvious that the time at which an event occurs cannot depend on the state of motion of the person observing it, until Einstein showed us otherwise. It's obvious that microscopic objects which are not observed behave in exactly the same way as if they were observed, until Heisenberg showed us otherwise, etc., etc. Every major revolution in physics has involved the abandonment of one or other assumption about the physical world which up to that time seemed just the most obvious plain common sense. Try to think what assumptions about the physical world have not so far been challenged. I would claim that one idea which has not been seriously challenged in any of these earlier revolutions is the idea that the past causes the present and the present causes the future. So I think my bet would be that if there's a really, really major revolution in physics sometime in the next 100 years or so, and my bet is that there probably will be, then I would bet that that revolution is in one way or another going to involve the abandonment of our current ideas about the arrow of time. Now, of course, the obvious question you will now ask me is, okay, well, what is this revolution going to be like, and what's the theory which comes out of it going to be like? And I can really only give you the answer which I'm told that the late jazz musician Louis Armstrong gave when he was asked by a questioner where jazz was going. And his reply was, man, if I knew where jazz was going, I'd be there already.
I just missed the final word about Louis Armstrong.
Oh, yeah.
His
so
answer?
His answer was, someone asked him where jazz was going, and his reply was, man, if I knew where jazz was going, I would be there already.
With you?
So I would be there already.
Already?
I would already be there.
Already?
Yes.
Thank you. Thank you very much.どうもありがとうございました。それでは、それじゃあ、質問時間にしましょうかね、まず。はい。まだ時間はたっぷり。それじゃあ、質問ございますか。考えていただけちょっとイントロダクションのところで、ご紹介のところで私はちょっと言い忘れたことがあって、京都におられるときに、湯川研究所で、プログレス・オブ・シオリティカル・フィジックスという雑誌、論文雑誌の編集に関わられ、編集といいますか、日本人の書いた英語の直すという作業をしていただきまして、それで後で日本人のために英語のノートというのを書かれまして、それは私なんかのそれについていろいろ勉強させていただいたということを、物理学研究室との関連でもしていただきます。それからノーベル賞は潮流度ヘリウムさんで午前中は詳しく話していただいていますが、2003年に受賞したんです。今日のお話でその我々の時間の進み方向の感覚が宇宙が今膨張しているということに究極関係しているんではないかというのは非常に壮大なアイデアだと思います。あと最後におっしゃったアインシュタインであるとかハイゼンベルトが相対論であったり量子力学を作ってきたようにまだ物理学でそういうことをさらに我々はそれと同じことを成し遂げる必要がある。それが一つヒントはレゲスさんがお感じになるのは時間と原因ですかね。時間の方向とそのコーザリティ、因果率ということに関する人類の今まで決まった考えをですね覆すような理論があってもいいんじゃないか。物理学としてはそれはあってもいいんじゃないかというお考えです。アームストロングさんジャズでジャズはどこ行くんでしょうか、これはどうなるんでしょうかという質問に対してアームストロングの答えは、それを知ってたら私すでにやっているというそういうことですが、そういうすみません、ちょっとだいぶ喋りましたが質問をお願いいたします。はい、どうぞ。
Okay, I'm Mr. Hayakawa of the Urbana Institute of Cellular Physics, and so your view is connected with the university expanding with time. The universe expanding. Sorry. The expansion of the universe is connected with a law of time. But somebody doing the experiment on the isolated system which still have some reversibility, and some theoreticians argued the reversibility of the isolated system without dissipation.
Yes.
So what do you think about such?
Well, I think undoubtedly that's true. If you, in principle, if I have an isolated system with a number of degrees of freedom, then of course we can on carrier occurrences and so forth. And in particular, if we take the usual then for a sufficiently long time, we will probably find that entropy can decrease in time. But I think in some sense, the interesting question is what will take us seriously.
Yeah.
And of course, partly the answer is that no system is ever completely closed, but also that we're usually interested in times of the order of laboratory times and so forth. And under those conditions, it seems that the second law of thermodynamics works pretty well even for a completely isolated system.
My name's Andrew Hillier, I'm from the Department of Astronomy. In your introduction from Mayama-san, you said that you started your undergraduate career studying philosophy. And I was wondering how this kind of philosophical grounding may have affected how you think about physics and kind of your work that you do.
Thank you. Yes, yes indeed. Well, I think it has actually profoundly affected the way I think about physics. As you know, philosophers tend to be a very, I think the English word is ornery, you might not understand that, so they tend to be very, very counter-suggestible, a lot of people. They don't, in other words, they don't take for granted, they deliberately refuse to take for granted what everyone else takes for granted. And so I think I probably have, throughout my career, been much more prone, much more ready than most of my colleagues in physics to challenge some of the basic assumptions we make about the physical world. One example would be that when I first started thinking seriously about the question around 1980, there was a quite, I'd say, overwhelmingly established view that it would forever be impossible to display the characteristic effects of quantum mechanical superposition and so forth at the level of any object you could reasonably call macroscopic. And had all sorts of hand-waving arguments to do with decoherence being given in the literature at that time. Now, there were various reasons why I started challenging this, but I think one reason I was ready to try to challenge this point of view was precisely that I had been taught by my philosophical training never to take anything for granted until it had been established by rather firm arguments. And in this case, I did not believe the arguments were sufficiently firm. And sure enough, now 30 years later, in fact, many of the effects which people said were totally impossible and ridiculous have now been seen.
ざっと下手な訳ですが、哲学のバックグラウンドがどのように物理に生かされているかというか特徴があるという、認められていることをすべてそのまま鵜呑みにしないという態度でずっとやってきているということだったと思います。So then, in connection with this question, do you intuitively think what's granted is not correct, or do you? Is this your intuition, which intuition is something like you take something granted, although without any proof.
Yeah.
But in that case, your intuition says intuition means without any proof.
If you like,
believe that what's taken accepted is correct, or do you intuitively counter-react what's accepted, or do you intuitively no?
Yeah, well, I think I would like to think that I don't simply react negatively to an idea simply because it's established. I'd like to think that I have some slightly better reason, but although it's established, the evidence for it may not be quite as firm as is often thought.
So, I'm sorry, my question might be, can you intuitively judge what's granted is correct, or what granted needs to be reinvestigated? Is this your intuition?
I mean, if if I really thought I could, then I think I've been making much more progress in physics than I actually am. That is, I mean, I think it's obviously one, in some sense, almost by definition, one never knows sure when one's intuition is correct. But, for example, Einstein had certain worries about the relation of mechanics and relativity, and electromagnetism. I don't think he could have known ahead of time that these objections were in some sense correct. I mean, they might have been answered by a further development of the laws of electricity. He did have a strong intuition that they had to be something in some sense more general and more satisfying underlying it, and of course we now think he was right. Similarly, let me give you, incidentally, I'm slightly veering away from your question, but let me give you an analogy. I don't myself believe that quantum mechanics is the whole truth about the universe. Again, that's an intuition, not something I can establish rigorously. But let me try to make a historical analogy. If we go back to the year 1875, let's say, in those days, people believed in mechanics, by what we would nowadays call classical mechanics. Right? They believed in the laws of mechanics and the laws of electromagnetism as they knew them, etc., etc. There's no experimental evidence against that. Against that picture, 1875. Some came later, but not in 1875. And yet, there was one very important thing that happened in 1875. Namely that Gibbs published a paper containing what we now call the Gibbs paradox. Now, the history isn't unclear, and I'm not entirely sure about this, but my impression is that Gibbs himself and his contemporaries really just looked on the paradox as a sort of minor accounting matter. They didn't take it terribly seriously. Had they taken it seriously, I think they would have been forced to conclude that somewhere between the level of everyday macroscopic experience, where the laws of mechanics have been verified and evolved, and the level of single atoms, mechanics, that is classical, as we now say, classical mechanics must break down. At some point, they would not have been able to foresee at what point it would break down. They would certainly not have been able to foresee in what way it would break down. But that it must break down, I think they could have reasonably foreseen. Now, I think we're in a similar position today with respect to quantum mechanics. I believe that the conceptual problems, like the famous Schrödinger's cat problem, are sufficiently severe that we can reasonably conclude that somewhere between the level of the atom and our everyday experience, quantum mechanics must break down. Again, we can't tell at what point it's going to break down, even less can we tell in what way it's going to break down. That it must break down, we can tell.
ありがとうございます。分かっているということと、それからイントゥイションで物理学者がイントゥイションという言い方します。それの関係についていろいろギブスパラドックスについての例を挙げていただきました。量子力学がブレイクダウンするということを、どういう形で証明されるのか、あるいはそういう手がいいのかというコメントいただきました。他に質問、物理学のあるいは哲学の質問でも結構ですし、そうではない、ノーベル賞に関する質問でも結構です。どんな質問でも、日本語でも結構です。はい、どうぞ。Please identify yourself.
Oh, I'm Takayuki Muranoshi from Kyoto University. You've been talking about free wills and so on. So I know two persons. One is my fiancé that say they can talk with ghosts and actually they tell them about their future. Okay, I have no choice whether to believe in physics or free will. But you know, this kind of experiment is quite unrepeatable. And the science, modern science, is repeatable experiment. So what do you think? Is the modern laws of physics still leave rooms to these unpredictable or psychological things? And maybe could this be the source of free will because every person's life is irrepeatable?
No, that's a very interesting question indeed, I think. In fact, in some sense, I'm tempted to believe in ghosts. Okay, now, so I have to define what I mean by that. generally in science, not just in physics, but in science more generally, I think we tend to classify, and I think your question did try to classify phenomena into two classes. That is, phenomena which are repeatable, given appropriate experimental equipment by any scientist under appropriate conditions, etc., etc. And then phenomena which appear to be, or which we claim are, in some sense, a function of the state of mind of a particular individual. And we think of these as illusions or fantasies or whatever you want to call them. That, there is a subtle assumption, I think. And that assumption is that there does not exist a class of phenomena whose realization requires both the existence of certain objective physical conditions and also an appropriate state of mind of the person who's doing the experiment or whatever. In the case of ghosts, obviously you need the right haunted house and the right date of the year, etc., etc. But, you know, some people just can't see ghosts, and as you say, others can. And so I don't totally dismiss the possibility that such a class of phenomena may exist. And indeed, I think that's, in principle, a very interesting direction in which science might in the future go. Right now, I think in some sense, the difficulty seems to be that, almost by definition, these experiments, as you say, are unrepeatable and uncontrollable, but there have been some rather serious attempts in that direction. I don't know if you know the book, for example, by John Hasted, called The Metal Benders. He actually did take a class of so-called parapsychological phenomena seriously, and he did do a series of experiments, and he did obtain apparently meaningful statistics of this. And so in his case, what he found, in fact, was that there were certain things which, of course, obviously did require certain physical equipment and so forth, but even given, basically this is the business of bending spoons inside boxes and so forth. And he found, at least as he reports, that okay, obviously you do need certain physical equipment, etc., certain physical conditions, but even given that, not everyone can do it. And he found, in fact, that his best subjects were almost always children of about 7 to 9 years old. You can make what you want of that, but as I say, that's what he reports. And I would sort of tend to take at least some of it seriously.
今まで物理学は再現性可能なものというものを扱ってきましたが、ちょっとそうではない、ちょっと認識にも絡んでいる、認識だけで現れるものじゃないものに対する扱いをどうするかという話です。他にどんな質問でも結構です。そちらにありますか。手を挙げておられる。はい、どうぞ。
Sorry to ask a second question, but in kind of your kind of history biography there, you said that you were in Kyoto University in 1965. And I mean, as someone who's here now as a non-Japanese person, I'm still quite a rarity, I feel. In 1965, it must have been even more of kind of a rare event.
I guess I was.
So I was kind of wondering how it actually came about that you ended up in Kyoto.
Well, by the kindness of Professor Takeo Matsubara, I guess. I developed a rather strong interest in Northeast Asian culture and history, and since it was not, all sorts of reasons, but one factor was that it was not possible in those days to go to China because of political factors, and so I thought I would certainly like to, in some sense, immerse myself in Northeast Asian culture and history, and where better to do it than in a place where there was good physics also going on, and that of course was Kyoto. And so I wrote to Professor Matsubara, and he very kindly admitted me as a member of his research group, his camp. It's been a very happy year.
松原教授は現在東京にお住まいだと聞いております。他に、はい、どうぞ。
Yoshitaka Tanimura, the chemistry department. So in the morning you said the curiosity is very important to throughout the science.
Yes.
But nowadays we are under the pressure of doing some useful things. or young students, they have to publish a lot of paper. Do you have any comment about it?
Alas, as you say, it's a fact of life. But, to get jobs, one has to publish papers. But I do think, now this is rather serious, I think, because probably there are, I imagine, quite a few people in the audience who are either right now at the postdoc level or will be at the postdoc level in a year or two's time. And I would myself say, okay, you do, sure, you have to recognise the facts of life. You have to recognise that in order to get apply for a permanent job after 2 or 3 years, as a postdoc, you have to have published a certain amount of papers, etc., etc. Well, okay, so you have to take that into account and spend some of your time simply, in some sense, doing things which you know or are very confident will result in published papers. However, I would also say, whatever you do, don't spend all your time doing that. Always set aside some fraction of your time, whether it's 15%, 30%, 50%, but set aside some fraction of your time to look at problems where you are genuinely not sure whether you'll ever get an answer. Those are the really interesting ones. I mean, the ones that you do, the problems that you do, knowing ahead of time that you will be able to get an answer, and almost by definition, they're boring. And the people who just count papers and so forth, they may or may not take note of them, but they will not really, they're not likely to be important contributions in the last resort. So, always set aside at least some fraction of your time. A question you just don't know that you're ever going to be able to solve, or anyone is ever going to be able to solve. You really should do that.
ありがとうございます。いつもなんか世知辛い生活にどんどんなってきてるようですけど、今日のこの特別講義のようなところに来ていただいてですね、ゆっくり考える機会を作っていただいたので、ありがたいことです。それをここに足を運んでくださった方はちょっとそういうね、普段の自分のやっていることからちょっと外れても大事なことを聞きたいというモチベーションにあふれた方だと思います。他にもうしばらく時間がありますので、せっかくの機会ですから、学生の方から、どうぞお願いします。Please identify yourself for some.
日本語ですみません。はい。理学部の1回生の湯沢と言います。
First year student, undergrad history.
時間について固定観念を持ってはいけないということがありましたが、時間がもしかしたら連続でないかもしれない、非連続的であるかもしれないということも可能性としてはあるんですかね。
You discussed the arrow of time, but is there a possibility that the discreteness of time is maybe important?
That could be, that could easily be so, but if it is so, then I think one can be fairly sure that it will be at a level which is much smaller than the scale which can be reached in existing accelerator experiments. I mean, it might well be that, say, at the so-called Planck scale, time indeed does have to be thought of in discrete units. What consequences that would have for some of the questions I've been talking about, I think is not entirely clear. My instinct is that probably it will not make much difference, but I don't know, it's not been much explored.
答えは大変いい質問です。連続ではないということももちろんあるかもしれません。で今分かっているところではプランクスケールという時間、それは何秒ですかね、時間にすると。プランクスケール、加速器の実験で現在理論がかかっているプランクスケールという、そこまでは連続であろう。しかしそこよりの向こうでは不連続性があるかもしれない。今ちょっと考えるにそれが不連続であっても、今我々が手にしている物理学にそれほど大きな変革というか影響はないのではないかと考えますということでした。
Thank you.
Sorry, I'm an undergraduate student from Kyoto University. So I'm a little bit nervous now, but I can't miss this only chance maybe in my life to talk with the Nobel Prize celebrity. Thank you. And I just want to ask some not very professional questions. Based on the knowledge I learned right now, I think that maybe we learn more. We will feel that in the physics, it become more close to the philosophy. Maybe we think all about it. It's not based on the experiments. It's made based on our intuitions. So how can we justify it? It is right or wrong?
Well, I don't think you really can. That is, I think that in the end, physics does have to be an experimental subject. And I think that, you see, I think this is a good example. We had, or most of us had, these intuitive assumptions about the world, which were in some sense really not directly based on an experiment. And what essentially John Bell did was to show us that if we put these assumptions together, we could make certain non-trivial predictions about real experiments. We did the experiments and it didn't work. And so we do know that one of these assumptions has to be wrong. Now, of course, it's possible, as I think was suggested earlier, that in some sense we should have known a priori that one of them was not justifiable, but most people certainly didn't realise that if it was true.
How can we conduct an experiment about times?
Well, that's a very good question indeed. As I say, this just shows the slipperiness of the question of the arrow of time. Because I can tell you these words about the possibility that the arrow of time may reverse or the arrow of causality may reverse. But then you ask, how on earth am I ever going to do an experiment to test this hypothesis? And at least right now, I don't think I know a way. I think perhaps if we think harder, we will find a way. After all, people were familiar with quantum mechanics for 40 years before Bell's theorem. In some sense, it was implicit there. They just hadn't dug it out. And again, and it may be that there are things we can dig out concerning the arrow of time, which are there. We just have to be especially clever.
ありがとうございます。実験で検証できないようなものを物理学が入っていったときどうしたらいいかという話ですけれども、今いくつか例を挙げていたというのは、よく考えると実験検証がどんどん出てくるというそういうアスペクト他にどうでしょう。最後の質問。どうぞ。
I'm 4-year graduate student and my name is Hinari Tanaka, and you said that you learned philosophy in Kyoto University and now you research physics for a long time, and I'm interested in, do you have any specific problem you are really interested in for your research life?
Well, for much of my research life, that is since, I did my PhD in 1964 and I started a full-time faculty position in 1967. Since about 1979, I have been very seriously concerned with this question of the validity of quantum mechanics as you go up from the level of the atom to the level of everyday experience. I mean, basically the problem of Schrödinger's cat. So I've certainly been very interested in that for a large part of my career. And of course that is an issue which in some sense does involve considerations both from physics and from physics.
So you were really interested in the basics of this world, like...
Yeah, so it's a basic question.
Thank you very much.
レイジさんの今までのご研究はいつもその量子力学のファウンデーションそちらの方を見ているということでした。じゃあよろしいでしょうか。もう一つ最後の質問で、はい、どうぞ。学生さんから。
My name is Ying Zhang. I'm a PhD student in Urbana Institute of Physics. So, I have a little comment on your topic of the era of the time. Because in cosmology, there exists some concept of the time which is divided into perhaps into two different definitions. One is called a global time, and then it's called local time. And in cosmology, there exists some space-time where the time can be just defined locally and not globally. So in this kind of space-time, so we don't know how we should say, for example, connect the time with the concept of the entropy or something like this. So, I don't know whether you have any comments on this kind of stuff.
I would have to say frankly that this is a very technical issue which I have not thought about or read about particularly deeply. I imagine that it's somewhat related to the question of wormholes, so forth, circular time. I mean, I think that certainly some of the, if indeed these possibilities are for real, then at some stage in the future of physics we're going to have to face up to the way in which they affect the kind of questions I've been talking about. However, I would just emphasise the fact that most of these, certainly most of the considerations concerning wormholes and so forth, only arise if you make the implicit assumption that our current understanding of say, general relativity can be extrapolated over scales many orders of magnitude beyond which it's been tested. Just as, you see, there's an interesting parallel there. The paradox of Schrödinger's cat only arises if you assume that quantum mechanics can be extrapolated from the level at which it's been tested, which at least until very recently was the level of single electrons and atoms and molecules, all the way up to the level of our direct experience. If that assumption fails, then there is no Schrödinger's cat paradox. Right? Similarly, if the assumption about the extrapolation of general relativity fails, then at least some of these the questions which you raise, I think, would in some sense disappear. So then it's a matter of taste, as it were, how seriously you take paradoxes which do require this kind of extrapolation by many orders of magnitude. Or whether you simply say, okay, let's wait and see if the extrapolation is right or not. Which of course is going to be, in this particular case, is going to be a long time.